So we now have all the ingredients that we need for a fully functional convolutional neural network. And the only thing we have to do now is adding the backpropagation part. However, that will be a rather long part of our particular lecture here, and will be a relatively long section. That's why I divided this part in smaller parts. And we want to start with the simplest layer, the flattening layer, and then also add the backpropagation part to the activation functions. Adding the backpropagation part to the pooling layer and also to the convolution layer will be a bit more tricky. So let me just start with the flattening part. So the only thing that the flattening layer does is rearranging the data. So it turns the 3D or ND matrix into a 2D object. And there are no derivatives. Nevertheless, we want to stick to the same notation for the different variables. So the incoming argument we still want to call d values, which is in our case the feedback from the dense layer, because the flat layer passes the information on to the dense layer. Then the dense layer performs backpropagation, and the inputs of the dense layer are the d values in the flat layer. And then we have to create the inputs in the flat layer. And as I said, there's no derivative. It's just rearranging the data again. And then we have the inputs as an output. And we can actually check that, because if we take the output from the max pool layer, put it into the flattening layer, it creates our 2D matrix. And if we take this 2D matrix and put it back into this backward method of the flat layer, we should get the same image back. And that's how we can check that the backward part of the flat layer does exactly what we wanted to do. So therefore, let me just move back to the other screen. And also I would recommend to add a new folder that we just call backpropagation. Again, just in order not to confuse it with the backpropagation chapter we discussed and the other lecture, which is the base of the current one. So I would just call it backpropagation again, and then we just copy and paste the current code so that we have something like an kind of version control. So we also still have the data from the previous run. I just want to show you the images. So this time I took another one. We had lots of cats, so now we have dogs. That's the input from the convolution layer into the max pool. And that's after the max pool. So that's the max pool output. And that's the mask. And what we should get as an output from the backward method in the flattening layer is this image. And we want to check this. So let's go to the flattening layer and just add the backward part. So we just go there and just say, just add the new method. So we just say backward self d values. And then we need a shape of our input. So we can just copy and paste that and then just say that's the shape of our input. So we can directly just say self input dot shape. And then we just set up the inputs. And again, that has to have the same shape. So now we write a loop that goes through the values matrix and reconstruct the n-dimensional matrix that contains the images with all the channels. So we just do kind of the opposite what we did here. So we just say for I in range, and then we have the number of images. Then we take the matrix, the inputs, and we take all rows, all columns, and all channels, and the particular image I. And then we take the values And remember, every row corresponds to an image. And all columns correspond to the information we have, so to the features. And we then just say reshape. And what you want to reshape, of course, X and Y of the images, and then the number of channels. And that's it. So then we can just create our output, which is the inputs. So let me just compile this code and also just run this code and test it. So we load the new network, the new module. Then we want to add the new max pool. And of course, we have to run the max pool first. And now if we just say flat backward, and we feed and we take the output from the flat layer. So what is the output from the flat layer? So that's the matrix then, would feed into the dense layer. So that's our matrix we would feed into the dense layer. And now we just put it back into the backward part. And that should give us the same image that we see here. So let's take a look at this image. So we just can actually save this first in an image. Let's call it test. All right. And let's take a look at the image. So if we just say plot, imshow, and then we have our test, all rows, all columns, channel 1, image 4, then we should get exact same image that we see here. Oh yeah, that was of course nonsense. So we want to have flat backward, and that creates the inputs. And this is our test. So that creates the inputs, and that's the image we return. So let me just take a look at the plot now. And now we should have the plot, and and you see it's the same plot. Of course, that's not a proof. So let's, for example, run this. It's all zeros. Yeah, and we can also just do that. So it works. Our backward part of flat creates or rearranges the image in the correct way. So whatever comes out of the dense layer as the input, it reconstructed correctly. That's what you see here. That was what this exercise was for. So the flattening layer works. And now we just go to our activation functions. So we recovered this image here. And we call it test, which is the inputs. And we saw it's the same image. All right, so now backpropagation, and then let's go to the activation function. So what was the idea always? So you get the values from the layer which is below the current one. In the current layer, you calculate the derivatives, multiply this inner derivative with the d values, and that's creating the inputs for the next layer, which is above the current one. So what is it, the inner derivative for a sigmoid? So you just go to the sigmoid function, look at the definition, and apply those rules for the derivatives. And I just want to show this once because you have to do this once in a while, and it makes sense to be fluent in that. So you calculate the derivative of this object, of this function. So you have 1 plus e to the power of minus x in the denominator, which gives you to the power of minus 1. That's where the 2 comes from, times the inner derivative, which is e to the power of minus x. And the inner derivative of that gives me a minus here, which cancels out with the minus I actually get from the denominator here. And when you see such a structure, you can see that the original function somewhere is hidden in our derivative. And it's pretty helpful to rearrange that a bit. And then you see that the derivative of the sigmoid function is just the sigmoid times 1 minus the sigmoid. And we can implement this in our code. So we then just get our d-values. We know that the output was the sigmoid. Then from the forward method, then we just multiply the current value with the 1 minus sigmoid, which is the derivative. Then we multiply the derivative with the d-values. And that's it. And for tangents hyperbolicus, it's the same idea. So if you look up the definition of the tangents hyperbolicus, to form the derivative, then you will see you end up with a similar structure. Then you have the forward part, and then add the backward part in the same way. So we have the tangents hyperbolicus here, which gives you the output. So you have 1 minus the output is the derivative. I added a none to num just to make sure that we do not get into trouble with the NINs. And then we can multiply the inner derivative with the d-values. And that's pretty much it. So we just go back to our module now in our code and just add those lines. And then we're also done with the backpropagation part here. So we go back to our sigmoid. So we have the dense layer, we have the flattening, and somewhere we have the activation functions. So we just add backward part. So we have the d-values, and then we know that the sigmoid is from the self output. Then we calculate the derivative, which we do with NP multiply and sigmoid. And then I want to just add those parentheses just to make sure that the multiplication works. And then we have the inputs. Which we calculate by multiplying the inner derivative with the outer derivative. All right. Let me just arrange that with more detail. So then we do the same for the tangents hyperbolicus. So we also add the backward part. And then calculate the derivative, which in this case is 1 minus self output square. And then also want to add a num, so none to num. And add itself the inputs, which is the multiplication of the derivative and the d-values. Sorry. Okay, so we have the derivatives, which is 1 minus the output squared. Then I add this line, then calculate or multiply the derivative with d values, which gives me the d inputs. And that's it. So the next step will be the max pool. And that's going to be a bit more tricky.